So, good morning, everyone. I'm Simon Collins. I'm the Director of Product Management at Abaco Systems. And I'd like to talk today about what we and the industry are doing to enable cutting-edge capabilities for our customers in open architecture systems. And it's nice to be able to give this presentation here at a VITA event. VITA, I think, is probably the granddaddy of all the open standards organizations, perhaps with the exception of IEEE. But everybody else, all the other open architecture groups and standards committees are really building on work that is coming out of this group. So very pleased to be here to do this today. So predominantly, the VITA products and VITA technologies that are being deployed are going into very, very power-constrained environments. And typically for Abaco, that's on vehicles of all types: ground, air, marine, space. And the constraint is the power that's available, but also the power that we can dissipate off the products. So the power dissipation is a whole different talk. I won't go into that too much today, but there's obviously a lot of effort that goes into that, and VITA standards that are helping in that as well. I really want to talk about what we're doing with the power that's available to us, driven mainly by developments in the commercial arena. There are fantastic strides now in performance advancement. So within that power budget, our technology partners are really scaling performance, and I'll show some benchmarks in a moment that show that power per watt is really increasing. Again, driven by commercial, we're seeing enormous advances in machine learning and artificial intelligence, and how those technologies are able to harness the processing power that's available. And I think that's an area that we're going to continue to see a lot of growth. We continue to generate data, so increasing RF A to D capabilities. The previous presenter talked about RF ingest. We're continuing to be able to capture more data. And then the problem, when you've got that data, you have to be able to move that data around. So again, it's the interconnect bandwidth and the connectivity between all the parts of the systems that need to scale. So within that power-constrained environment, I don't think we've ever been able to generate as much data and process that data. But for our customers to be able to harness that, really, the drive towards open standards and interoperability is really, really key. And as I said, VITA being almost one of the original open standards organizations, we're now seeing higher level interoperability standards on top of the VITA standards that we all develop to. And that really accelerates the deployment of these capabilities by virtue of that interoperability. So in terms of performance gains, these are some benchmark figures. As ever with benchmarks, there's an enormous amount of nuance in how the benchmarks are done, what's being done. But across a set of products, these are Intel processors in the 2017 to 2023 range of age of processors. You can see an enormous scaling up. And that's benefit that we get year on year by the work that Intel does and continues to do. And so the three sets of graphs are different data set sizes. And you can see, obviously, the newer products are performing significantly better. I think there is a talk on benchmarking later. So the number with a T after it is the number of threads that are being used in the benchmark in this case. But you can see the set on the right-hand side, really performance quite low. But when we put a GPU into the mix using the same benchmark, you can now see that that right-hand group with that large data set, the GPU really comes into its own. We're seeing in this set GPUs integrated within Intel parts and then discrete GPUs. And one of the things that really is interesting is that on the right-hand set, we have OpenCL and then CUDA. Sorry, it's the left-hand set. You can really see that the gray and brown colored bars where the optimized data set is used, that there's an enormous performance gain. And then the data set on the right, the large data set, you can see now a significant improvement in the parallelization within the GPU, getting that performance boost. So on that one data set there, you can see a number that goes above 2,000 gigaflops, so 2 teraflops. And just to put that into perspective, the first supercomputer in the world ever to cross that 2 teraflop performance threshold was Sandia National Labs ASCII Red in 1999. So 25 years ago, to get to 2 teraflops, you needed a room full of very, very high-end, highly interconnected parts. And that was really available to an extremely small set of programmers and researchers to make use of that. And now that 2 teraflops is in a VPX card that we can deploy in a conduction-cooled environment in a vehicle. So it's a staggering performance gain that's happened. We expect that performance to carry on scaling up within the power constraints that we all live with. Of course, in the world of supercomputing, this is pretty small by current standards. So much bigger sets of systems, very, very fast interconnect. And so they're still powering away exponentially, and I think we won't be able to keep up with the rate of improvement because of that size, weight, power constrained environment we have. But nonetheless, very, very impressive. So one of the probably most exciting use cases of all of that processing power is going to be in artificial intelligence. We're already seeing customers deploying AI, and we're seeing that in ground vehicles and in airborne as well. And some of the more obvious applications of it are in identification, so target identification, target tracking, segmentation from within the data set. And we're seeing customers doing that on imagery, so standard visible spectrum, infrared. We're seeing customers using artificial intelligence on RF data streams to pick out specific features and specific events within an RF stream, within a radio stream. And we're seeing that on radar as well. NVIDIA really is leading the industry in terms of the raw performance and the tools and usability. And the caveat is there are other vendors, and so we see certainly at a lower power point, actual wattage, we see other vendors' technologies being used, so Intel and NXP, for example. So artificial intelligence is really, really effective at getting a very, very quick turnaround from a new threat or a new feature that you want to be able to identify and pull out of your data. It does need significant data to do that training. And so we're seeing people using synthetic data, so generating their own data and then supplementing that with real-world data off the vehicles. And the other thing that is a pretty significant trend is the need to be able to use that data safely. So it's highly statistical and need to be able to really ensure that the action you're about to take based on the data you think you've just seen is true and coherent. And the safety is really being led in automotive and industrial, and the aviation probably a little bit slow to catch up, but the FAA and EuroCai now have working groups to address bringing artificial intelligence into aviation. We spoke about RF performance increases. So the amount of data that we can ingest from the RF streams going up all the time, increasing the sample frequency, increasing the channel count, increasing the resolution of the sampling, and then pushing that into FPGAs to do the initial processing, and then moving that data to a back-end processor, typically an Intel processor. Some of the things that we're working on there is in terms of synchronization, so multi-chip synchronization on a single board, and multi-board synchronization so that you have a coherent data set and a coherent view of the data that's coming in. And then in terms of connectivity, we're generating more data than ever before. That's got to be moved within the system. Image courtesy of TE connectivity, so the RT3 really allowing us to get to very, very high bandwidth connectivity across the backplane. So the multi-gig RT3 is now allowing us to get 100 gig Ethernet across the backplane, which even a few years ago was terrifying most of the signal integrity experts at Abaco. And then moving beyond that for optical, so being able to get these high performance signals out of the chassis and from chassis to chassis, system to system, and also the coaxial to the backplane. Again, a Vita standard driving that. So those are the backplane connectivity that we're implementing in products today to allow all of this data to be moved between products within a system to system. And that, as I say, is allowing us to get to 100 gig, and we have now 100 gig Ethernet doing line rate over the backplane or optical. That said, 1 gig and 10 gig, we still see a prevalent across systems in our space, and I'm sure for a very long time we're going to see connectivity through 1 gig and 10 gig. But the things that are starting to impact now within Ethernet switching, time-sensitive networking. So, and it's an evolving set of standards. It's IEEE 802.1. But the idea is to have a very deterministic, low latency communication over Ethernet. There's an aerospace profile in development, and that gives very bounded latency and will allow for mixed traffic in the same network, but highly protected. And then the other trend is in multi-domain networks, so physical separation, where VLANs are not accepted, then physical separation for black and red enclaves. So we continue to see that moving forward. And then just to pull that all together into a single system. So this was a system put together for a demonstration at AUSA last year, where we have software-defined radio integrated in the same system as the command and control, the tactical comms. And you see that it's all here running through a common Ethernet switch, but we need to be able to ensure that the traffic is segregated correctly and that we're able to guarantee transmission of the right data to the right place at the right time. In that demo, the compute-intensive SBC and the GPU payload were actually performing an artificial intelligence on video. We have artificial intelligence on the RF input as well. Wasn't shown in this demo. But this is very typical of the systems that we see our customers putting together based on the common standards that are being built at the core level by some of the groups like IEEE, building the Ethernet standards that our technology partners, so Intel, Xilinx, NVIDIA, Broadcom, build upon. And then, along with your good selves in this room, the Vita standards, building that into boards. And then above that, we have things like SOSA, excuse me, CMOS, MOSA host, putting in place the interoperability that allows our customers to rapidly take a set of core technologies, deploy them into a real world and fast deployed application. So I think this hierarchy of industry standards is obviously working well. It's going to continue, and it's good to see that the standards above the CMOS, the host, are calling upon and calling out explicitly the Vita standards, and rather than going and inventing new standards and causing probably some headaches for us if they went that route. So year on year, we're seeing the performance increasing. Swap C, so size, weight, power, and cost, is going to continue in its current envelope, but we're happy that we're able to allow our customers to deploy new capabilities every year. We see that continuing for the foreseeable future. Thank you.